Today we are going to do section 4.7, Maxima Minima. Now that is identical to what we did in Calculus 1, okay, where you find the maximum of something or the minimum of something. Now first we repeat the same concept as we learned before, the critical point. Now what is a critical point? A critical point is when f is defined at an open set that contains a certain point. In other words, the point has a neighborhood of f. Okay, it's not a boundary. Now, in that case, the point is critical if fx and fy are both 0. Okay, and that it would make it critical. There's another option is that if fx or fy isn't defined, then it's who knows what that is. But mostly we don't care as much when they're not defined. They're not even defined. What are we supposed to do? We're mostly concerned with when they are 0. So critical points for the most part means both fx and fy equal to 0. In other words, you have a level spot. Okay, if it's all differentiable, that is, then you have a level spot, and that is likely the maximum or minimum. Of course, there's also that possibility where you have, you know, the graph just goes level, like x to the power 3, where the graph goes level a little bit and then keeps crawling up. That's also possible. That's why it's only a critical point, and we need to investigate it some more to see what it is. Is it a maximum, minimum, or neither? Right? So let's look at example 4.38. Please do that as part of your homework. We're just going to find critical points. So to find the critical point, of course, let's look at the next page, 439, where you take the derivatives, right, and you solve for something. Now remember, both fx and fy need to be 0, which means you have two equations that will likely land you with a point or two. And so you find out some kind of a point, and then you figure out if it's a maximum or minimum. And then of course what happens? There's also a concern of well, there really isn't. You just do that. Okay, take the derivative and figure out what the critical points are, and let me move on. Oh, I should also mention that in example 4.38, you might have a situation when you divide by a bunch of stuff, so the denominator cannot be 0. If the denominator is 0, then it's automatically a critical point. So yeah. So anyway, having said that, let's move on to the following page, which is the 441, where we talk about the local maximum and local minimum. Now that is the same thing as we've always understood it, okay? It's just the local bump, and where it might has a local mountain top or local valley, and then you have, that would be called the local maximum or minimum. And then either one, however, there's a name for both, and it's called the local extremum, and which is, I believe, the same as the previously learned in one dimension in Calculus 1. So, and then look at the bottom of this page, we have a theorem that says, let's see, my page is stuck. Okay, now the theorem which says that if you have a function z equals to fxy, our surface, is defined and continuous on an open set containing some point x0, y0, and then the partial derivatives also exist at x0, y0. So they're not undefined or anything like that. Now, if that is the case, if f has a local extremum at x0, y0, that is, if it's either local max or local min, then x0, y0 is a critical point. In other words, x0, y is a critical point. In other words, the partial derivatives are 0 at that point, because they are defined. So it's not like it's possible that you don't have to worry about them not defined. Therefore, if it's a critical point, then the partial derivatives are 0 at that point, for any local extremums that at x0, y0. And so now, having said that, let's look down following page, where we look at the the saddle point. Now, saddle point is something that's similar to that thing in 2D where y equal to x cubed, where you crawl up, go flat, go level slightly, and then keep crawling up again. A saddle point is similar in that in one side you're going, like my hand here, one side is go up, both fingers, but the other side, the rest of my hand is going down, see? So that's called a saddle, yeah, right where, right where this part, see, this part is going, if you consider this point, this part is going down on both sides, whereas on this direction is going up on both sides. So it's neither a local max or local min, even though it has the partial, it is a level area, right? The partial derivative at that point would be 0. So then, so that would be called a saddle. And then let's look at the next page. We are looking at page 443, where we consider the second derivative test, which is very similar to what we learned. There are similar tests in one dimension in calculus 1, same thing, right? You have, you take the second derivative, and then if it's concave up or concave down, it means something. Anyway, this is the same way, theorem 4.17, where you pull out something called the determinant, and then you calculate, which is the second derivative, except this time is the partials, okay? fxx, fxy, and fyy. Now, if you calculate that, the determinant, which end up being something, then if it's bigger than 0, it has, and fxx is bigger than 0. There are two conditions. Then it has a local minimum. If it's bigger than 0, fxx is less than 0, it has a local maximum. If it's less than 0, it is a saddle point. If it equals to 0 for some reason, then you got nothing. Okay, you don't know, you've done it all for nothing. So that's the way it is. And here is a 3 nice pictures of the points, right? We have the local minimum, as you might imagine, local maximum, and the other thing is the saddle point. Anyway, those they draw the local minimum kind of the same. They should be different because it could look like anything, really. Anyway, so then we'll use the second derivative test to look at example 4.39, where you use the second derivative test to find something. Part A, where part A and B, okay, two surfaces, and you're going to figure out what? The local extremum. That is, which one is the local max, which one is the local min, if it has one, and which one's the saddle, and stuff like that. So you're going to be doing a lot of partial derivatives, which might be slightly tedious, right? But eventually you get to the point, you will calculate, you will be able to round up what the local extremums are. But that's not the end though. That's just on the inside. Well, the problem here is you even have to walk along the edge. I wanted to say crawl along. You don't have to crawl. You have to walk along the edge. Is it this problem? Now let me see. Never mind. You don't have to crawl along the edge yet. We'll do that a little bit later. This is just asking you for the local extrema, which is much better. Okay, so you take the derivatives, figure it out, and plug it in the values, and set things equal to 0, and so on, and then stuff comes out pretty readily. So please do example 4.39 as part of your homework. Next, let's look at page 447, the extreme value theorem. What that means is the same thing as we learned in calculus 1. The extreme value theorem says that a continuous function on a closed and bounded set attains an absolute maximum or minimum value at some point. Well, in fact, both. Okay. Now that is very important to know here is the closed and bounded. Now we're not going to really test you on when things are not closed or bounded, but think about it. Things has to be closed. This is true in 1D case in calculus 1 as well. If it's not closed, it might the thing might take off to infinity. Okay, right in your own set because it's not closed. If it's not bounded, it also might take off to infinity while your domain is too big. Okay, like any function, right? As long as it is most functions like y equal to x squared, for example, if you don't restrict its domain, it eventually gets infinitely big. So the function has to be both closed and bounded. Okay. Now if and continuous on the whole thing. If that is the case, then you'll be able to reach the absolute maximum value somewhere and the absolute minimum value somewhere. So next, let's consider with finding it. To find the extreme value of a function in a closed and bounded set, you have two things to do. First, you have to find the extreme value inside the domain, and secondly, you have to find the extreme value along the edge. That's because the extreme value inside, it might not be as big or small as the extreme values on the edge. So that's, well, the same as the 1D situation. So then, so what you're gonna do is a huge amount of work. Not only do you have to find the local max and the local min, you have to walk along the edge of the boundary, I mean the domain, okay, your limited, closed, and bounded domain, and check the value of all of them and see where the maximum and the minimum along the boundary is. And you're going to do that by defining the boundary in a parametric value. That is, let's look at example 4.40. Please do that as part of your homework, but we're going to look at it. For example, what is, let's see L1, okay? L1 is part of the boundary. We're looking at the following page. What page are we on? 448, okay? So L1 is, where's L1? L1 is the bottom line, okay? The bottom of the line, that's L1. And as you can see, L1 is to be represented by, where's L1? Some equation, xt, gt equals to, okay, what you're gonna do is plug in, now let me figure out what I want to say. Now L1 is simply some line along the axis can be parameterized by the equation xt equal to t and yt equal to 0. Okay, then you plug this xt and yt into the function f, the original surface, and that gives you a function of this thing along the edge. And then you're going to take the derivative to figure out when this thing has a maximum or minimum, which that gives you the value of the maximum or minimum along that boundary alone. Okay, now by now you can see where you're going. Now, not only do you have to find the local maximum and minimum inside the boundary, you have to find all the maximum and minimum along the edge by representing the edge with some kind of parametric equation and plug it into your original surface to figure out where the boundary maximum and minimum are. So all that translates into a lot of work actually, but please do it patiently and get it all done. And to do that, you just pretend that you're not doing one problem, you're doing 5 or something like that. Okay, so by the time you patiently get through all of that, they are tedious, but they're not particularly hard. It's just you're just taking derivatives, just like what you're doing. It's like going back to calculus 1, except now you have to do 5 problems for one problem. And so eventually you will get through all of it. Each line needs to come up with a parametric equation for it. And in this case, it's just a rectangle, so the equations are not as hard to come up with, but it might get harder, right? But in the meantime, so eventually you're going to find out where is the local maximum and minimum. So I have, and there's a bunch of results, okay? The local, eventually you find out what the absolute maximum and minimum is. And I will show you what I plotted on the Decimal 3D. Now what I plotted here is, as you can see, we have the function I have up here, okay? And then I plotted the plane z equal to 17. That's the local minimum of the graph. If you plot it in the 3D and you look around, you will see that the local minimum is also the local maximum. And then that one point in that one tallest corner there, that's obviously the local maximum. So we could get around it and say, why don't we just plot this thing on there and, you know, and we wouldn't have to crawl along the edges and figure out all this junk and work so hard. You can do that, and that would make sense for this problem. But think about it. This is for a c equals to f of xy, two variables, which you can then represent in a graph in the surface in 3D. What happens when you have three variables? Then decimal 3D is not going to save you. You know, this trick is not going to work. So it's important to learn how to do this on a 2D basis, even though we can do this, right? But we can't do this if you have three variables, 4, 5, 6, 500. Then you know how to handle it. If the data you can't, there's no way to. Once you go beyond two variables, and the third one, then you can't depend on decimals anymore. In fact, you can't even visualize it because we are 3D creatures, right? We don't know how to visualize anything beyond that, but we can still work on it exactly the same way. And you can find maximum, minimum for functions with, I don't know, a ton of variables and with the exact same trick, and which is why it's good to do this thing. Not too many times, but once or twice is very good for you. So please do this homework. What problem is this? Whatever this problem is, please do this as part of your homework. And then the next, this problem 4.40. Actually, this problem has a part B, and it's the same thing. Let's flip over and look at part B. This time the domain is a circle, it's inside the circle. So then what you're going to do is find the local max or min, which you can do it fairly readily with the partial derivatives setting it to 0. But then you have to claw along the entire edge of the circle, which means you have to parameterize the circle, okay? And then plug it in, take the first degree derivative and setting it to 0, and so on and so forth. And your book has typed in a whole bunch of numbers, which I don't think is necessary. Just, solve it. It's a simple trigonometric equation. Well, when I say simple, I just mean there's no calculus in it. You're still going to have to do quite a bit of work. But anyway, so if you grind through this stuff, okay, and then you can calculate and figure out what are we doing again? Oh yeah, the local maximum and minimum. Now let's look at the next page, 452. Where you have your book give a graph of this thing, I think, but I don't think that graph is very good. Okay, so I drew a different graph that I want to show you. Now, please draw this graph yourself into the decimals calculator so you can take a look at it. Now here is the function is in red. That's that surface there, and then what I did is I drew the circle, which I extended into a cylinder, right? I drew the circle around it so that you can see exactly how that works. The intersection, which you can kind of see because I have the decimals on translucent, which means see-through. So you can see right past it and see how the intersection goes. And so that is, okay. And that is the circle for it. Now, I should mention that to do this, you have to get this graph to look nice. You have to change the values of the range of x, y, and z axis, and also uncheck the xy plane because then there's too much stuff. See, get rid of the xy plane. It helps seeing things better. So that's how I did that. And see the translucent surface on top, the check mark. Yeah, if you check that, then you can sort of see through things. So then you can, see better. Okay, all the different surfaces. And you can see that the circle on the bottom is the domain, and that goes up, and the intersection is where the graph really is. That is the graph only, the actual surface is whatever you see inside that cylinder. Okay, what's outside doesn't count because its domain is restricted. Now let me show you another picture of the same thing. Come on. Now another view to draw is I disabled the cylinder, so now you only see the intersection on top and the bottom, the domain, which is on the bottom. The intersection, as the book figured out, is a parametric curve, okay, this one right here, which looks like looks like an ellipse, right? Anyway, it might be in the same plane. It looks that way. But anyway, please type this thing into the Desmos 3D and look around it and enjoy it a little bit. As you can see, the domain, which is the circle at the bottom, okay, as with the radius 4, the actual surface is just whatever is inside that long green circle, this one right here, which I copied down from the book. And it's something that you have to, I don't know if you have to, I think, well, I don't know. Well, I know the book figured it out, okay, what that intersection is. So I typed it in. As you can see, it fits very nicely. So, yeah, so please type in the Desmos use the Desmos calculator and enjoy looking. You can turn this thing around and enjoy how to use the calculator and admire the surfaces and visualize how they might be in 3D. The last example, which is on page 452, is yet another problem of the same kind of thing. Then you have some kind of a conic section kind of a surface, I guess, or just some surface. And then you are supposed to calculate the maximum and minimum along a prescribed limited domain. Okay, in this case, looks like a rectangle. So you have to do everything we did in the previous section, which is going to take a while, as you can see. But if you stick with it, you should be able to get it done. Okay, so please do that one as well. And then we have come to the end of this section. For homework, please do page 456, problems 319, 25, 33, 37, 41, 45, 49, 51, 53, and that's it. Okay, now for problems, let's see. Okay, for problems 49 and 53, I have some hints that you can consider looking at if you are stuck. But I recommend not looking at hints, but first look at your problems a little bit, try to hit it without the hint. And then if you're stuck, then feel free to look at the hint. And so please go do your homework. And when you come back, I want to talk about some of the problems. So now that you're done with the homework, let's talk about some of the problems. First, problem 349. Now that problem, you have a surface, then you're supposed to calculate the distance between I think the surface and the origin or something, right? But anyway, it sounds a bit tricky. So how would you do that? This surface, then the distance from any point to the origin, of course, you calculate it by the Pythagoras theorem. So then eventually I realized all you have to do is rewrite the equation of the surface where you have x squared equals to 5 plus yz, okay, which is over here. Now once you've done that, what you do is you set the distance squared, which is x squared plus y squared is z squared, right? And which we'll call it b. The reason is because we don't want the square root, okay? The square root is annoying. If we can, because as long as we can figure out what the maximum or minimum for the square root of the distance, then we know the square root is the same point, okay? So we're maximizing b, and that's enough to be maximizing d, is what that means. So therefore, we're going to plug x squared into here, and we get this equation, which is very easy to take partial derivatives of. We set it to 0, as we are required to do, and then come up with some relationship that very quickly we realize that means one thing: y and z are both 0. And then you plug it into the original equation. If y and z are both 0, that means x squared is 5, okay? X will be plus or minus 5. And then, so plus or minus 5, 0, 0 is your answer. I checked at the back of the book. And the distance between that curve and, that surface, and the origin, the closest distance, is 5. And then I plotted this surface into Desmos 3D. Here it is. And you can see that it's a cute looking surface, very neat. Okay, so please plot this into Desmos, and then I also plotted. You notice that you just have to type in like that. Okay, x, y, z equation. It doesn't really matter. You don't have to worry about independent variable, dependent, whatever, implicit, none of that matters. You just type it in and out pops the surface, and this thing's smart. Anyway, so what I also did here, is I typed in the circle, x squared plus y squared equal to 5. So that's the circle, which you notice the circle touches the surface exactly at where x is plus or minus square root of 5. Okay, so which proves that that my solution is correct. See, pretty neat. So please plot this into the Desmos calculator, the 3D calculator, so that you can move it around and see what it does. And so that's the end of that problem. Okay, next we're going to talk about problem 351, where it's a simple problem similar to what we did in Calculus 1 practically, but I'll talk about it because it's slightly interesting. Okay, so you have the length plus twice the width and height equals to 108. Okay, so then, well, we'll just plug everything in. The volume, of course, is length times width and times height, and then you plug that L in there, and then you take the partial derivatives, and eventually, when you come out looking something like this, then you eventually realize the H and W has to be the same. It makes sense that they are the same because look at the equation. They're symmetrical. One's not different from the other, right? Who's to call what's width and what's height? So if they're the same, then you quickly figure out what the length has to be, and that should be the right answer. So that answer is correct. So next, let's look at problem 353. And that is the problem of the distance between some surface and some plane. Now, first you might look at it and feel puzzled, like how would I do that? Well, the first trick you do is figure out the distance between the plane and some point, which is on page 198, okay, where you have that formula where the distance is qp dot n, where n is the normal vector for the plane. And so if all that sounds rusty, just look it up, okay? And refresh yourself what that formula means. Like what is QP, what's N, and how do you come up with N? N is basically, see, I have N written down right here. N is basically the coefficient of the plane, okay? And you notice N is 1, 2, and -1, corresponding to the numbers in front of X, Y, and Z. That's all N is. All right. So, and then Q is a point on the plane. Okay. Any point on the plane will do. So, being that our plane is simple, we'll pick the point 0, 0, 0, which make our problem much easier. Now, P is a point on the surface. Okay. So then we'll pick X, Y, and then Z, of course, is X squared plus Y squared plus 10. So that is our point for P. And then we calculate this thing from Q to P is all the coefficients of P subtracted by Q, being that Q is 0. Then QP is the same thing. See, QP is looks the same as P itself because Q is at the origin. So we follow the formula and do the dot product. Okay, here's N. So we're gonna do the dot product like the formula says. And then we come up with something, okay, and then what is that? Oh yeah, that's the distance. So we finally come up with a formula for the distance, and the formula is not that bad, right? We'll keep the magnitude of n on the side so that we don't have to think about it. Okay, so we'll call it big D. So that we'll take the partial derivatives, and notice that the partial derivatives there will be 2 of them. There is that is the distance is equal to plus or minus of this thing. The reason is because the formula has the absolute value here. So you have to worry about a negative version as well. But not for long though, because very soon you realize that whether it's positive or negative, you're going to set the partial derivatives to 0 anyway. So it makes no difference whatsoever if it's positive or negative. Either way, because it equal to 0, then either way the x will be 1/2 and y equal to 1. And with that, then you came up with the right answer. X is 1/2, y is 1, and then you plug into f of x or y and came out with z equals to 11¼ Now at this point, I look at the answer in the back of the book, and they look completely different from mine, which made me very puzzled, and I looked over and tried to figure out where I got it wrong and all that stuff. And so here's the answer at the back of the book, okay? Now that looks so different than from what I have, and no way are they the same, right? But when I checked it out, then I realized, I looked at the question more carefully, I realized that the book asked me, where is the closest to the surface is closer to the plane? I have to give the location on the surface and the location on the plane. Okay, so that's what happened. He eventually figured out that the location on the surface is this thing I calculated, which is not wrong. The location on the plane is actually this thing which I calculated by I put the surface into a parametric form, which looks like this. Now, if you don't remember how to do that, or what that even means, please look at page 187. It's very straightforward. What you do is you take this point here. Where's my point? 1/2. Why does it say that? Doesn't matter. The point is x is 1/2. Okay, you multiply, you plus t. The coefficient of t is the same as n. Where's n? Yeah, 1, okay? And then y, well, y is 1, right? I calculated, and then you plus 2t. 2, where does 2 come from? 2 is the y position for n, so it's 2t, etc. z is minus t because value minus t because it's minus 1. So anyways, please look at page 187 if you don't remember what this is. We are parameterizing, what is that? A plane. Yeah, well, something. The point is we need to figure out where the plane and the vector, the line, intersect. Okay, so once you do that, well, I mean, parameterize. This is not the plane. Sorry, this is a line. Okay, this is where the line intersects the plane, the vector that we're talking about. So then when you plug everything in, plug this t, okay, into this plane equation, then you come up with something as t equals to this number. And once that happened, these numbers will come out. So the plane, the surface, will be closest at this location, x, y, z, whereas the plane will have x, y, z on this location, where it's closest to the surface. So that's where all those funny numbers come from. Now, I also plotted this thing on the calculator, and I ask you to do the same. Let's see. Yes, here it is. Okay, now here's my plot. Let me move this. All right, so as you can see, here's my two surfaces. There is the x squared, z equals to whatever. Okay, that's my surface. And then here's my plane in blue. And then here's the vector. Okay, here's the vector that starts at a point on the surface and ends at a point on the plane. As you notice, it hit the plane at a certain point, and I drew a vector at that point too. And as you notice, I don't know if you can see it clearly enough. As you notice, the two vectors coincide on each other, so they are the same. I mean, what I mean is my vector is hitting the plane at the point that it's supposed to, right? So then, I even did the fraction numbers in decimals. See, as you can see, t equals to 35 over 24. I calculated it this way. You just push this button here if you need it to be like change it from decimal point to fractions. So it's very, very convenient. And you can always copy and paste in here, so you don't have to type the same thing again and again. Now, so please graph this thing in the decimals calculator, and let me give you a hint. Now I have now to graph this thing properly. Now you notice that my vector is supposed to be normal to both surfaces. Okay, the distance between two things are normal. That is perpendicular to both surfaces. As you can see, it does look like that way. But when I first plotted it, it didn't look that way because I forgot that x, y, and z axis has to have the same range. If you don't, then the thing will be squashed, and then things don't, 90 degrees no longer look like 90 degrees. So at first I was really puzzled as to what is happening to me, right? But eventually I figured it out, and it all looks very nice. Okay, so please figure out the details, like such as where do you want the x and y to be, okay? And whenever you graph something on the graphics calculator, you might type in the right equation and then you can't even find it. Where is that thing? And eventually you found it and it's very small in a corner or looks weird and narrow and bad. So you need to adjust the range of x, y, and z. That is, adjust these numbers in here to make everything come out looking peachy. So with that, let's so please do that too as part of your homework. Work on the decimals calculator. It's a lot of fun, I think, to do this kind of thing. And you can turn it around and see how it looks in all directions, right? So yeah, and that marks the end of this section.